Time response analysis is our next topic that is to be discussed. The name itself is very clear, response of a system with respect to time. So, we need to analyze systems of first order, second order for various inputs that should help us to modify or improve the performance. Any analysis should lead to design. The time response is given by C of t, and this is given by C of tr plus C of t steady state. Time response mainly consists of two parameters: response in transient period and response in steady state. So, this is transient response plus steady state response. To understand better what exactly transients, what elements causing transient response, let us consider a simple example that a resistor with some switch is excited by some voltage source, say V, this is equal to 10 volts, say R is 2 ohms. Then when the switch is closed at t equal to 0, the switch is closed, then there will be a current that flows through the circuit. V is 10 volts, then current is 10 by 2, so it is 5 amperes, and that 5 amperes also somewhere on the axis. So, it is instantaneous. The current in resistive circuit, this is 0, so it reaches to 5 amperes in 0 time, and the steady state current is 5 amperes. Now, I will add inductor to this. I will add inductor to this element with the same arrangement, no change in other parameters. Now, I have a resistance of same 2 ohms, some L, some inductance is added, it may be millihenries, and this V is as usual 10 volts, and the switch is closed at t equal to 0. Then what will be the current in the circuit? So, this current in the circuit, current will build up in the RL circuit, and that current is given by V by R into 1 minus e power minus t by tau, where tau is the time constant of RL circuit, L by R. Now, if you see that now response I of t as a function of time, for 10 volts is the supply. So, current here V by R, V is 10, resistance is 2, 5 amperes into 1 minus e power minus t by tau. That means, I can write this as 5 minus 5 e power minus t by tau. There are two terms involved in the response current in RL circuit. One is 5 and the other one is there is an exponential decaying term. So, you can see that the response will definitely reaches 5 amperes like resistive circuit, but it takes time now. It takes time, and that depends on the time constant. Significance of time constant is how much time it takes for the current to reach 5 amperes. So, now I will draw that the response in an RL circuit will be like this. So, you can see that there is an exponential increase for certain time, that is given by 5 e power minus t by tau, and as time approaches infinity, this term will be vanished, means the transient part, the exponential term in the response is a transient part that is going to be vanished as time approaches infinity, and the next response is a steady state response that will remain even after transients are died out. So, you can see that this transient response is this minus 5 e power minus t by tau. So, how fast it goes and reaches steady state value is decided by the time constant of the circuit, L by R. So, plus 5. So, I define this term in the total time response. In the total time response, I of t or C of t is transient response plus steady state response. Remember, transient response is going to be vanished very fast or very slow, that depends on the time constant. So, this is not there as time approaches infinity, and this 5 will remain, and then the steady state current, it is called steady state response. So, in this RL circuit, when it is closed, switch is closed at t equal to 0, for this voltage there will be a current to build up and reaches 5 ampere steady state. Once it reaches steady state, this inductor acts as a short circuit. So, though inductor is present in the circuit, but it acts as a short circuit because current is established and reaches steady state amperes. So, as long as it is 5 amperes, no change in the supply voltage, that inductor behaves as short circuit. Anyway, this is the time response. I can say it is a first order system and it consists of two parts, steady state response and transient response. Now, let us consider an RC circuit. Instead of an inductor, let me put capacitor. Across the same circuit, same voltage. Now, switch is there, closed at t equal to 0, R is equal to 2 ohms, and there is some capacitance, maybe in microfarads or millifarads, and same voltage of 10 volts. Now, here instead of inductor, I connected now capacitor in series with the R. Now, when the switch is closed at t equal to 0, there will be a current in the circuit and voltage across the capacitor starts building up. Let us assume that voltage across the capacitor is V naught. So, this one is V into 1 minus e power minus t by RC, where RC is the time constant of RC circuit and this is given by 1 minus e power minus t by tau. So, this also consists of two terms. You can see one is minus V e power minus t by tau plus V. So, this part of the response is transient part, transient response, and the response that remains after these transients have died out is steady state response. That means, the capacitor is charged to the supply voltage V or Vi in this way. So, how fast this response reaches steady state depends on R and C of the circuit. That is why time constant means what? It is the indication of a system how fast the response reaches the steady state. So, time constant RC will decide how fast this voltage reaches to the rated voltage. The moment the voltage across the capacitor is equal to the input voltage, the current stops, because the value of resistance is very small and it is connected only to charge the capacitor. So, this voltage and this voltage are same, then there is no point of current flow because potentials are same. So, the nature of the current in an RC circuit is initially the capacitor voltage is 0, it acts as a short circuit. So, the current in the circuit initially V by R, that means it is 5 amperes, it is 5 amperes, and then it slowly decays, and finally by the time this capacitor is fully charged to this voltage, the current becomes 0. However, this is also a first order system. If you have R and L or R and C, it is nothing but a first order system because it creates one pole. If you see the transfer function of this RC circuit, we have discussed in the previous class that V naught of S by Vi of S, for this RC circuit you have got 1 by RCS plus 1, means RC is a time constant, so 1 by tau S plus 1. So, that means the pole is at S is equal to minus 1 by tau. One pole means first order system. If there are two poles, second order system. So, this response also you can see there is a transient part and steady state part. So, if you take only resistor alone, there is no transient response because instantaneously the current reaches to steady state. If you add inductor, there is a delay. If you add a capacitor, there is a delay. So, it indicates that energy storage elements, maybe inductor or capacitor, will create transients. If there are no energy storage elements, there are no transients. So, there is no system, electrical or mechanical system present without energy storage elements. That is the reason why a time response of any system will definitely have transient response and steady state response. Let us consider now a second order system where it consists of R, L and C. In the previous slide we have seen that either inductor or capacitor were alone with resistor, but now if you combine L and C to the R circuit, now the voltage across the capacitor is response, that is V naught of S, and input voltage is Vi of S, and now if you see the current I that actually flows through this R, L and C, and voltage across the capacitor will be developed, and if you see the transfer function of this V0 of S by Vi of S is 1 by LC S square plus RCS plus 1. We have seen in the electrical systems transfer function that you have obtained this. What it indicates? There is a second order term. So, the number of poles of the denominator, it is known as characteristic polynomial or characteristic equation. So, it indicates that when L and C are added, it is forming the second order system. If only L is there, no C, then it is first order. So, that way two energy storage elements create second order system, means number of poles in the system are increased to 2. Now, such a system is excited by some input Vi, say again it is a steady state value, finally it should reach. If it is a first order, the response we have seen that it is increasing this way, but if it is a second order, again it depends again on the components R, L and C. Let us say for some values of R, L and C, the response will be like this, means here also there are transients. Transients are there in first order system as well as second order system. So, oscillations indicate that they are not permanent, they will remain in the system only for short period of time. So, this is called transient response, and the response that remains after transients have been died out is called steady state response. So, we need to analyze the time response of a first order system and second order system in terms of some specifications, and then let us see how to modify the system to give best performance. So, as I indicated in the time response analysis, generally it will be given by, for electrical system, V0 of s by Vi of s, and in general it is represented by C of s by R of s. Now, that is given by some system, it may be a transfer function of a system. Then if I want to see or get C of t, that is time response, this is in Laplace domain. So, you need to apply inverse Laplace transform to get this. So, before getting C of t, what you have to do is C of s is equal to R of s should be taken this side, this side. So, R of s into the system, that system is in the form of transfer function. So, R of s, what is meant by R of s? R of s here is nothing but input. So, you need to give some input to the system to find the response. So, once R of s is multiplied by transfer function, you get C of s, and here you need to apply inverse Laplace transform to get C of t. So, that C of t probably we take, and we will try to analyze to improve its performance. So, what kind of inputs we give in the time response analysis? As we have discussed even in the earlier classes, that there are 4 standard test signals, inputs available to test the performance or to see the response. So, that inputs are step input, ramp input, parabolic input, and then impulse input. Impulse input. So, these inputs we need to see, we need to give these inputs to systems of first order, see the response, and give these inputs to second order system and see the response, C of t. So, certainly as I indicated just before, that response will certainly have transient part and steady state part. We need to see that for various inputs. There is a definite relation exists between these signals, that is impulse signal is actually Laplace transform of the impulse signal represented by delta of t is 1, where impulse indicates what exactly the impulse? Impulse is a very high magnitude in 0 time, ideally speaking, but the practical impulse is a very high magnitude in very short time. If I say the magnitude is high, A, very high, then the time here is 1 by A, means the area of the impulse is 1, A into 1 by A is equal to 1. So, that impulse, Laplace transform of that impulse is 1. Now, we have seen that step signal also, how is it represented? It has a magnitude of A, for t t greater than or equal to 0 and its magnitude is 0 for t less than 0. So, A, Laplace transform of A is 1 by s. Laplace transform of A is A by s. Now, if it is a unit step, it is equal to 1 by s. Remember, A is some magnitude. So, Laplace transform of A is A by s, and if it is a unit step, it is 1 by s. So, how is the step represented? Step signal is a change, sudden change. So, this is A. As a function of time, step signal is A, magnitude constant with respect to time, and this is equal to 1 if it is a unit step. So, you can see that signal is there for t greater than or equal to 0 and no signal for t less than 0. Now, if you see the ramp is given by a into t. So, this signal exists for t greater than or equal to 0 and this is 0 for t less than 0. Ramp is indicated by straight line passing through origin. So, this is signal with respect to time, ramp signal. Ramp signal is represented by at for t greater than or equal to 0 and the signal is 0 for t less than 0. It is represented by a straight line passing through origin, ramp signal. It varies linearly with respect to time. Now, the Laplace transform of this ramp signal at is a by s square. Laplace transform of this ramp function is a by s square. If it is a unit ramp, this is equal to 1 by s square. Laplace transform of ramp, unit ramp is 1 by s square. If you take the last signal, parabolic signal, it is given by a t square by 2 and this is the signal for t greater than or equal to 0 and it is 0 for t less than 0, parabolic signal. These are the inputs we need to give here, multiply with the transfer function to get response, because our topic is time response. So, Laplace transform of this a t square by 2 is a by s cube. So, now you just see the beauty of the relation that exists between these signals. Laplace transform of impulse is 1 and Laplace transform of unit step is 1 by s. Laplace transform of unit ramp is 1 by s square and Laplace transform of parabolic is 1 by s cube. So, you get integration or differentiation. The relation exists between these 4 signals. If you know some response, you can find out another response by integrating or differentiating. So, that way all 4 signals will have some internal relation that helps us to find out the response for some input if you know the response for some other input.